Hello students, welcome back. We just completed section 3, graphical description. Now let's go to section 4, numerical description of data. One way to describe a data numerically is to take the average, or we call it the mean. How do we do that? It's easy. Add up everything and divide by the total. Please recognize this data set is the same data set you have been using. By the way, there is a subtle difference between sample mean and population mean. The computational formula is the same, add up everything and divide by the total. But for sample mean, we use Roman character. For population mean, we use Greek character. Typically mu because m for mean and Greek version of m is mu. The reason? Population mean is a parameter. Here's a reminder. The data from population is called a parameter, and we use Greek letters, mu, sigma, pi, those kind of things. Data from samples are called statistics, and we use Roman characters, m, s, p, and so on. Here we are using m versus mu, or it's very common to use bar instead of m. So whenever you see bar in statistics class, it is very much likely it is talking about the mean, the sample mean. If you see a mu, then it's really highly likely it is a population mean, a parameter. Okay, so much for mean. And now the next topic is median. A median is a middle number. Here's an example. Again, let's stick to the same data set, but this is sorted, smallest to the largest. And then remove smallest and largest, smallest and largest, smallest and largest, and then what's left in the middle, merge in, that's a median. Let's go. Smallest out, largest out, and then next smallest out, next largest out. I'm a bit tired of doing this, so let's do it 3 at a time. Those out, these 3 out, these 3 out, and then these 3 out, and then these 3 out. Okay, what do we have? In the middle, we have 77. That's the median. It's easy. Whenever you have sorted data, just knock off the first, last, first, last, first, last. Or if you're a bit tired of doing that, do it 3 at a time, 4 at a time, and then maybe in the end you may have to slow down. Whatever it is, you have the middle number, and that's the median. Now, you have 23 scores here, so that's odd number, so we have a middle number, so that's a median. But if you have even number of data, in that case, you're going to get 2 middle numbers here, and you have to take the average of those 2, middle of those 2. You see? Here I have 6 numbers, and knock off the smallest 2 and largest 2, and then we're going to get these 2 green numbers. And the median is the middle of the 2, the average of the 2. So average of these 2 versus median of this data set, they're the same, 3.807. Please check. Now, one of the nice things about median is means are affected by outliers, but medians are not affected as much. Consider this. We have those 6 numbers, and the median is going to be the middle of these 2, so we have that. And the mean is sum of all these 6 numbers and divide by 6. Somehow, somebody made a mistake and then mistyped the decimal point, and then you wrote 41.27 here, and then just calculated the median and mean without thinking, and then mean was affected heavily because of the 41.27, but median, no, it stays the same because it was crossed out at the first crossing. Now, what if you make mistake here in the smaller part? Instead of 3.492, it became 3,492 and moved to the right. That's going to affect the median, yeah, but not as much. Mean is affected heavily. So if you expect some outliers, then medians are much better representative of your sample or your population or whatever, your data, than the mean is. So if you go to, say, real estate website here in Dallas County, then you'll see some median house prices in that community instead of mean. You can expect some outliers there. For example, if there's an abandoned house or something, then that one house will affect the mean heavily. I mean, the home price of that abandoned house will be pretty close to zero, or maybe negative even. Also, if you have an income distribution or something, then there are so many extremely rich people, so it's better to use median than mean. Now, the next topic is quartiles. Basically, it's median of median. So here we go, sort out data. Okay, sort out data. And then this is the median. We did that, okay? And what do you do? Excluding the median, we take these numbers, the lower half of these, and then take the median from here. Also, excluding the median, we get these upper half, and then take the median from here. How do you take the median? The same deal, knock off the smallest and largest, smallest and largest, smallest and largest, and then in the end you get the middle number. So median of upper half. So that's in 1/4 position. That's called the first quartile, Q1. And you do the same thing. Median is 1/2 position, and then the median of upper half is going to be in 3/4 position. And that's going to be the third quartile. So it's the same as doing median computation twice. Now, there are two ways to do that. One way is to do it like this, exclude the median, and then take the lower half and the upper half. And this is a textbook's way. Our textbook is written that way, if I remember correctly. I'm using too many textbooks at a time, so sometimes I get a bit confused, but I think I'm right. Sullivan's textbook, Johnson and Kubi's textbook, and there are many more. And also Devona's textbook, I think they're all the same thing. But in some cases, people do it a little bit differently. They include the median. And then do simple computation, knock off smallest, largest, smallest, largest, smallest, largest, kind of like this. I want decimal expression, not... Okay, that's better. Mathematical's default is fraction expression. I change those decimals. Okay, all right. So, depending upon how we set up the median, if we exclude the median and then get the lower half, or if you include the median and get the lower half, you get different result. Median excluding the, first quartile, Q1 excluding the median versus Q1 including the median. And this one is Q3 excluding the median, Q3 including the median. Oh, which is right? Actually, they are both right. Depending upon circumstance, depending upon textbook, or depending upon culture, you may use one or the other. And if you use MS Excel, by the way, I'm going to show you MS Excel in section 5 in separate video. And there is quartile INC and quartile EXC. Quartile including the median versus quartiles excluding the median. So both are correct. So whatever you use, I'm going to give you full credit. So don't worry too much about it. But Mathematical's way to deal with it is kind of like this. quartile excluding the median, and quartile including the median, and then take the average of the two. And this is Q1 and the most sophisticated method. So you do both of that, excluding the median, which is our textbook method, the most preferred method as far as this course is concerned, and medians or quartiles including the median. Okay, this is acceptable too, with full credit. And then this is the best. Take the average of the two in the end. And if you use quartile command from Mathematica, this software that I'm using, it does it this way because Mathematica is really sophisticated calculator. That's what advanced quartiles are talking about. I marked it as an optional topic, but I think it's okay. It's a little bit narrow topic that I understand, yeah, but at this level, at 3000 level, I think everybody will be able to understand it. Okay, so much for quartiles. Now there's something called percentiles, and just a name only. And this is the number where all those numbers lower than that has a certain percentages. For example, the median is 50th percentile. First quartile, Q1 is 25th percentile, Q3 is 75th percentile, and say for example 10th percentile is lower 10%, so that's going to be even more, even smaller, and 5th percentile is going to be even lower, and first percentile is going to be even lower, and so on and so forth. And if you have something like 97th percentile in your, say, SAT score, that's great. That means you are top 97% or top 3%. Okay, we have sufficient time, so let's talk about 5-number summary. 5-number summary is an effective way to represent a data set with just 5 numbers. And these 5 numbers are the minimum, the slowest, and Q1, the first quartile, and the median, and then Q3, the third quartile, and the highest, the maximum. With these 5 numbers, you can make a good representative of entire data set. And this is a bare bone minimum, basically. And with these 5 numbers, it is customary to create, I'm not going to talk about mid-range and inner quartile range. No, never mind. I was going to open the box whiskers chart. With these 5 numbers, it is customary to create a chart like this, and that's called a box whiskers chart. So what do we have here? We have a box, and then a line at the median, and then we have whisker, and then at the end we have minimum, and whisker here, and on top we have maximum. This one corresponds to minimum 33, and that top whisker corresponds to maximum 94. In this data set, 33 is the lowest and 94 is the highest. And then the median is 77. Okay, here, the line here, the white line. And most of the pictures I saw have black line, but here in Mathematica, it gives you a white line. I don't like it very much. Black is a little bit more conspicuous. And then down here, at the end of the box, and at the top of the box, we have Q1 and Q3. That's called box whiskers chart. And almost every semester in exam 1, I included box whisker chart problem in the exam. Both box whiskers chart and histogram in the exam, as a matter of fact. Sometimes only one of them, but most of the time I wrote both of them. I believe those two are important. And box whisker chart can be either vertical like this or tilt and horizontal. Personally, I like to have vertical, just like I prefer to have vertical boxes and histograms. But if you tilt it and do it sideways, that's fine too. I don't mind. Okay, so much for the 5-number summary and box whiskers chart. One more comment, one final comment here. the 5-number summary, in my opinion, is a bare bone minimum. So if you want to have some numerical description of a certain data set or graphical description of a certain data set, this, I think, in my opinion, is the bare bone minimum. Mean or median by themselves, just one number that's representative of something like a 500, is not very good, in my opinion at least. I think this should be bare bone minimum. Why am I emphasizing that a lot? If you go to histograms and produce an histogram, how many rectangles are appropriate? Well, it depends upon the size of the data set. And if you go to your textbook, there's some magic formula which I don't remember, and that gives you the minimum number of rectangles that you have to get. But the theory behind it is actually non-existent. It's just a convenience and custom. So why don't I replace that with something simpler? The bare bone minimum is 5. If you draw less than 5 rectangles in histogram, I'm not going to give you credit, because histograms should be more extensive than bare bone minimum. And this is the bare bone minimum. At least histograms should be better than 5-number summary. So if you have fewer than 5 rectangles, then I'm not going to give you credit. Of course, if you use that magic formula in the textbook somewhere, that's going to be better, but it's complicated and I don't even remember. Let's see. Do we have enough time to complete it? Let me try. Variance and standard deviation. Okay. This kind of thing is called sample variance, and this kind of thing is called sample standard deviation. What do? Let me expand fonts. Each datum minus the mean and square it. So basically I'm measuring how far away x1 is from the mean. So if it is far away from the average, then this square will be big. If it is pretty close to mean, then this will be small. Same goes to x2. If x2 is far away from x bar, the mean, then this subtraction square will be big. And f2 is pretty close to x bar, then this will be small. And of course we are taking squares, so you cannot get anything negative. You're adding it all up and taking the average. And instead of dividing by n, we have to divide by n minus 1 because it has something to do with degree of freedom. And the average is already selected, so what's left is just n minus 1 numbers. That's the reason. Anyway, take the average like this, and that measures how those x1, x2, x3, those numbers that dispersed away from the mean. So if each of the squares are big and on the average are big, and that means they're more spread out. And then on the other hand, if this quantity is small, that means more concentration toward the center. And that kind of thing is called variance. Take the square root of that, and that's called the standard deviation. These are just stupid computations, so I'm going to leave those computations to you. If you try to calculate this thing with handheld calculator, it's going to drive you mad. So I'm going to tell you how to use MS Excel for this kind of computation, or how to use Mathematica using technology. There's something called population standard deviation, which we're not going to deal with very often. And that is how spread out those things are for the population itself. But in practice, it's nearly impossible to calculate because this capital N value will be really humongous. But here, there's no n minus 1. For sample variance, there is n minus 1. And what they do, the same thing. If the data or if the population are more spread out, then bigger standard deviation. And smaller standard deviation means more concentration toward the middle. Alright, so much for section 4, and then we're going to do some example problems using technology in section 5.